in class. I know you don't want me to spend too much time on introductions, so let me get started right away. I'm going to be proving a theorem. Remember this theorem? We define d of x to be the GCD of two polynomials, a of x and b of x, where these polynomials have coefficients in some field. The field is arbitrary. I'll call it f adjoint x. And then the claim is that there exist polynomials, let's call them s of x and t of x, so that we can write d of x as a linear combination of a of x and b of x using s of x and t of x. Okay, so let's try to figure out what the proof is. The idea is to follow the same idea that we did for integers. For integers, remember, we started off with some sort of set S, and which were linear combinations. We made sure the set S was not empty. We only took positive combinations and then took the minimal element. We do something similar here. We'll let S be the set of all linear combinations. So a of x, say u of x, plus b of x, v of x, where u of x and v of x are polynomials. And these are polynomials, so let's let S prime be the set of all degrees of these things. So I'll call them degree of f of x, where f of x is in S. Now these are all positive integers, or non-negative integers. So S primed, okay, maybe I'll write that down. S primed is a set of non-negative integers. So it has a minimal element. Say m. And that means there exists some polynomial f of x in S with degree m. Now f of x may not be monic, so let's multiply, or let's divide by the leading coefficient to make this f of x monic. This new f of x, this new monic f of x, is also in S of x because when we multiplied through by the inverse of the leading coefficient, we can take that into our u of x and v of x, and so that element is in the set S. Now what we'd like to do is show that f of x is equal to d of x. It's the GCD of a of x and b of x. So first of all, f of x is a linear combination, so we're good there. If we can show f of x is d of x, then we'll be finished, because then it's already a linear combination of a of x and b of x, and that was our claim. So to show this, we first of all note that, to show that it's a greatest common divisor, first of all we have to show that it's a common divisor, so we want to show that d of x divides a of x. So, f of x divides a of x. And we'll do it this way. If not, then we can divide f of x into a of x to get a quotient and a remainder with r of x not equal to 0. And because we've done the division, we know that the degree of r is less than the degree of f. But the claim now is then r of x is in S, contradicting the degree minimal. Remember, we chose f of x to be a polynomial with minimal degree in S. So why is r of x in S? Well, that's because r of x is equal to a of x minus f of x q of x, and f of x was already a linear combination of a of x and so we get here a of x, just sort of factoring 1 minus u of x qx, and then plus a b of x times a minus v of x q of x. And so this is inside S. And there's our contradiction. Thus, f of x divides a of x, and similarly, f of x divides b of x. So it's a common divisor. Now to show that it's the greatest one, to show us the greatest one, we just take any one. So let's let c of x be a common divisor. Then c of x divides a of x, and c of x divides b of x. But then c of x divides any linear combination of a and b, but in particular, remember we wrote this as our f of x, which means that the degree of c is strictly less than the degree of f. So f of x is our GCD. And we already have f of x as a linear combination of a of x and b of x. And so we're done. Thank you. I will post pictures of these notes, so even though this is all kind of shaky on this thing, I have to write on the paper and look at my phone at the same time, sort of thing. I'm sure I didn't do it very well. I will post pictures of these notes. Thank you. See ya. Bye.